Hi. Now that we've learned that definite integrals can be interpreted as areas below the functions, let's discuss some properties of integrals. And once we do so, we will be able to calculate definite integrals quite easily and use them to actually find the areas below or even in between functions. Okay, so let's start with property number one. Property number one basically says that integral from a to b f of x dx is equal to minus integral from b to a f of x dx. Look, what has happened over here? I've changed upper and limits of integration and introduced minus up front. Okay, first I'm going to prove this rule, which is actually very easy. And then we're going to discuss what does it mean. Okay, look, by definition, definite integral like that is equal to f of b minus f of a. Look, if I'm going to take minus outside the parentheses, outside the brackets even here, right? This inside, by definition, is an integral with limits b and a, which finishes the proof. Now, but how could we interpret this fact? Okay, let's see something very simple. Look, let's get to a situation where we have a function like that. Okay. Now, let's just say that we are interested in what is the area in between A and B. And look, let's figure out for a second, let's remember, let's refer to our previous video on how do we calculate this integral. Look, we do it by finding all the infinite number of these rectangulars, which are so extremely thin, right? Now, what is the size? What is the length on horizontal axis of one of those? Well, it's dx. Now, we know that this number is very small, right? But is it positive or negative? Well, it's clearly positive. Why? Because with dx, we are always assuming we are moving to the right. When we are moving to the right, to calculate dx, we take some bigger number and we subtract some smaller number, right? Of course, in this case, this is so tiny, we wouldn't know how to even choose those numbers, but still, we can be sure that this is positive. And look, how do we calculate it? dx times the height, plus 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 dx times the height, right? So, what we get as a result, of course, is a positive number, because all the heights here are positive. When we multiply positive number by another positive number, we get a positive number. But look, what would happen if we were interested in what is the area between point C and A. Look, again, the x's over here represent movement to the right? So they are positive. But now look, all the heights over here are below x-axis. They are all negative. Now, if we multiply positive number by negative number, we will get negative number. So look, if we would add all those negative numbers, we would end up with negative number at the very end. So look, this would cause a problem because size, area, cannot be negative. But if we would calculate it using definite integral, we would definitely get a negative outcome. So what could we do here to get outcome that is positive? We can use the property number 1. And instead of calculating as we did over here, integral from C to A f of x dx, we could reverse the situation. Look, we could go from A to C. And look, if we go from A to C, the x's are now becoming negative. Because look, we are moving from bigger to lower number. From bigger to lower. From bigger to lower. So, the x's are becoming negative. And now, negative and negative gives us positive number. So look, in order to get positive outcome in a situation like this, good thing would be to reverse limits of integration, just like we did over here. So in this case, I would recommend calculating integral from A to C, like that. We will use this property very, very often later on, but for now, I just want you to understand where does it come from. Look, by definition, we know that integral is a limit of a sum, right? And because here we have positive dx's, here we have positive heights, we get positive outcome. But over here, we've got negative heights. With positive dx's, we will get negative size of the area, which is not a good thing, let's just say. Well, area should not have a negative size. To overcome, there is plenty of ways to which we can overcome this, but the easiest, and let's just say the most elegant, would be simply to reverse the limits of integration, and by doing so, remember, we are moving in the opposite direction on the x's. The x's are now becoming negative because we are moving from bigger to lower values. Okay, so now we are ready to go to property number 2. And property number 2 says that integral from A to A f of x dx is equal to 0. Okay, another rather puzzling result. Well, first, again, let's start with the proof. Proof is, again, extremely easy. Well, again, we can use definition once more. By definition, this is going to be f of a minus f of a, which of course is 0. So the rule definitely works. But how is it possible? Okay. Okay, so look, we've got some function, and I'm interested now what is the area below this function above A? And usage of definite integrals, but even the definition of definite integral is showing us that this should be 0. But I see something here clearly. Look, again, this is because when I draw something, I need you to be able to see it. But again, what is the size of A? A has got no mass. A has no mass. So A, if we imagine it as a rectangular, what is the side of this rectangular? Well, basically, it is 0. Point has got no mass. Look, we do not even have enough to get dx over here. There's nowhere to move. So, if one side is 0, if I multiply it by any other number, I will still get 0. So look, because below one point, above one point is so tiny, it doesn't even have a mass. So the area above this point also must have the size of 0. Okay, and let me illustrate this to you with a very simple example, actually from theory of probability. Okay, it's January in Poland, right? If I would ask you, what is the probability that tomorrow's temperature is going to be 3 degrees Celsius? What would you say? Like, you might think, oh, there is at least some probability that temperature might be 3 degrees Celsius. Some of you might say 5, 10, 20. Some of you, maybe even 80. But the thing is, the true answer to this question is 0. There is 0 probability that tomorrow's temperature is going to be 3 degrees Celsius. When I'm saying that, probably most of you think that my answer here is ridiculous. But it can happen. Well, it can happen that tomorrow is going to be 3 degrees. But is it really likely? Think about it as that we've got a thermometer. Okay, I'm not an artist, but I hope you get the gist. And let's just say that here we've got 3 degrees Celsius. Now, there is a probability, you might say, maybe tomorrow on the news, they will say the temperature is actually going to be 3 degrees Celsius. But actually, it's rather unrealistic to think that actually this is the temperature that it's going to be. Because look, temperature might be just as well 3 degrees Celsius, 0.00001, right? Even though, in approximation, this is 3 degrees Celsius, it is not exactly. Look, because, look, how many points there exist between 3 degrees, 0.0000001 Celsius, and let's just say 2.99999999999. How many points is there? Well, if you would like to calculate how many points is between these two, well, there is only one conclusion. There is infinite of points. So look, if you would like to calculate the probability that one specific temperature is going to happen, so probability of 3 degrees Celsius, what would you have to do? You would choose one number and divide it by infinity. Right? How much would we get? Well, we would get 0. And basically, this is the same idea. Because, look, this point is so tiny in relation to what is around it. Doesn't matter how small is the neighborhood we talk about, we will always get 0 as an answer. Okay, so those two properties are rather theoretical. The rest of them are going to have more applications and are going to be more useful to us. But I hope those two properties are allowing you to understand the nature of integrals a little bit more. Okay, so now let's move to property number 3. Okay, property number 3 basically says that integral from some a to d f of x is equal to dx is equal to integral from a to b f of x dx plus integral from b to c f of x dx plus integral from c to d f of x dx. Look, what is this property telling us? That instead of calculating integral over some entire interval, we can divide this interval to some parts. Here in the example you've got just 3, but actually you can do it with, you can take as many as you want, but usually the best way to think about it is to take as many as you need. Of course, here we are assuming that A is smaller than B, smaller than C, and smaller than D. And look, for example, if we would have some function that looks like this, how could we, what would be a good idea to divide it up? Look, probably to choose some A, B, C, D, C, D, E, and F. And look, if we are supposed to find the area between the function and the x-axis, so we need to find this, and this, but as well as this and this. It would be better to calculate those areas separately, add them up, and then do it separately for those. And when we would be calculating those, it would be also a good idea to reverse the limits of integration. Because without it, of course, we would be getting negative numbers over here. And look, this theorem allows you also to deal with less usual cases. For example, look, the integrability theorem basically said that if we want to calculate definite integral over some interval, the function should be continuous. But for example, step function is not continuous. So if I want to calculate integral from A to C, I wouldn't be able to do it over here. But what could I do? I could divide this into 2 areas, right? And I could first calculate the integral from here to here. So I would first calculate an integral from A to B. And and I would add to it an integral from B to C. Now you might say, but this is problematic because we calculate B twice, right? We have B here and B here. But again, referring to property number 2, what is the area over here? Below this B, 0. Below the function, this function at B, 0. And below this function at B, also 0. So, not a problem, not an issue. And look, this gives us a very practical use, a very practical tool that we can use when we integrate, when we try to find the areas below the functions, because it allows us to divide a function into some specific areas where we can find the integral more easily. Okay, so now let's move to property number 4. Okay, and property number 4 states that integral from a to b out of negative f of x dx is the same as integral negative integral ab f of x dx. Look, actually I could prove it quite easily, but let's prove more general case of this. The case of integral of k of f of x dx, which, as you might guess already from our knowledge about indefinite integral, is equal to... Okay, how to prove it? Well, it's not that complicated. Look, taking what we know, about indefinite integrals, what we're going to get over here? We're going to get k f of x b a. After substitution of appropriate letters, we're going to get f of b minus kf of b minus k f of a. If I'm going to take k out of brackets, I'm getting k f of x dx. And look, if I would substitute k with -1, we would just get this specific case that we've got over here. Okay, now let me just show you 2 more that also generally follow straight from the rules on indefinite integrals. So, for example, if we property number 6 says that integral from ab out of f of x plus g of x dx is equal to integral from a to b f of x dx plus integral a b g of x dx. Look, here the proof would be just as easy as in the previous case, as long as we know the rule of indefinite integration that we've introduced previously. Please try to do it at home. I don't think it should bring you any difficulty. Okay, and let's just do one more, and after that we're going to move on to the examples of calculation of definite integrals. Okay, so the last one is associated with the integration by parts. Okay, so how would it go? So we've got integral x given by a equal to a and x equal to b out of v du is equal to u v x equal to a x equal to b minus integral u dv with x equal to a x equal to b. Okay, let me just explain. Look, this is the formula with integration by parts. For integration by parts, just here are appearing those x's. Why they are appearing here? Because remember, even though we are translating the this expression into expression with v and u, or v and du, we still need to finally transform it back into x, and by this token, of course, we need to substitute a and b for x, not for any other variable. Okay, so those are all the rules we needed to take care of. Okay, now let's do a couple of examples. And I think just a couple of examples should give you a gist how useful integrals can be in finding those areas, and actually how easy it is to use them. Alright, let's start with something for which we wouldn't even need to use integration. But let's start with function y equals x. Okay, this function looks like that, right? Straight line going through the origin. And look, let's just say that I want to know what is the size of the area below this function between 0 and 1. So what is the size of this triangle? Okay, how can I calculate it? Look, it's fairly easy. All I need to do is to calculate integral, definite integral from 0 to 1 out of x dx. So, first indefinite integral, x squared over 2, 0, 1, which gives us 1 over 2 minus 0, right? 1 over 2. This area is 1 over 2. Does it make sense? Well, of course. Like this creates a square, 1 by 1, so half of it must be 1 over 2. And what if I wanted to know what is the size of the area between -1 and 0? Of course, you might say, well, it should be 1 over 2 as well. It's not very complicated. But look, if we're going to write it down properly, there's one thing we should do. Look, here we see that this area is below x-axis, so everything here is negative. So here, our dx's were positive. We were moving in this direction. Now we need to reverse the direction of dx's, going from 0 to -1, and by doing so, we will obtain positive area. So we get that this is integral from 0 to -1 x dx out of x squared over 2, nothing changes here, -1, 0, this is 1 over 2 minus 0, this is 1 over 2. Okay, I'm using examples, a lot of examples that I'm going to be using is with 0 and 1 because they are easy to calculate. But of course, look, we can do it everywhere. For example, if I want to know what is the size of this area Again, all I need to calculate is an integral from this time 2 to 3 x dx. Again, well, indefinite integral here stays the same, nothing changes. We've got 3 over 2, 3 and 2, just as limits of integration, and now, so I have that this is 9 over 2 minus 4 over 2, and this is 5 over 2, or simply put 2.5. Okay, now let's see what would happen if we had quadratic function. So, now our function is y equals x squared. So, that function looks like this, and it's not beautiful, but it doesn't matter. Okay, so first I want to know what is the size of this area over here. Okay, so I calculate definite integral from 0 to 1 out of x squared over dx. So, indefinite integral is x cubed over 3, and we've got 0, 1. So we get that this is 1 over 3 minus 0, this is 1 over 3. Now we get that the size of the area between 0 and 1 below x squared is 1 over 3. Now if I would ask you, what is the size of this area? I hope you can guess by the symmetry of this function, it needs to be also 1 over 3. But now, see, the thing is that here, unlike in this case, this part is above x-axis. So we don't even need to change the limits of integration. We just calculate it as -1, 0 x squared dx. So this is x to the power of 3 over 3, 0 -1, which gives us 0 minus -1 over 3, which is 1 over 3. Okay, let's make things slightly more complicated, right? Let's start. Let's see what is the area below the function, below the cubic function. Y equals x to the power of 3. So, this function looks like that. And it's over here. Okay. Again, I am interested in what is the area from 0 to 1. So I hope at this moment it is self-evident to you what we should do. We start by calculating indefinite integrals, so x to the power of 4 over 4, 1, 0. We get that this is 1 over 4. Minus 0, which is 1 over 4. And I hope you can see some pattern over here. Look, for x, we had 1 over 2. For x squared, 1 over 3. For x cubed, it's 1 over 4. Then, for x to the power of 40, it would be 1 over 5. And so forth. So, you can see the pattern very clearly over here. And similarly, if I want to know how much is here, well, again, I should change the limits of integration. But of course, we know how much is it, right? But let's do this one last time before we find something more challenging. We go from 0 to -1 to avoid negative outcome. And this is 1 over 4. Okay, so let's try haven't done yet. Okay, how about y equals e to the power of x? So, e to the power of x looks like that. It goes through 1. Okay, and let's start with this one. So what is between, again, what is between 0 and 1? So what is the size of this shape? Okay, so here we have to calculate definite integral from 0 to 1 out of e to the power of x dx, which is simply e to the power of x 1, 0, which gives us e to the power of 1 minus 1, e to the power of 0 is 1, so this is e minus 1, so approximately 1.72. But of course, this answer is good enough, right? It's actually more precise than this one. Okay, and now how about here? How much do we have here? Again, I don't need to even change the limits of integration, right? Because we are above the x-axis. So again, that this is negative 1, 0, e to the power of x dx, which is simply e to the power of x, 0, negative 1. I get that this is 1 minus e to the power negative 1. So this is 1 minus 1 over e. Okay, let's try maybe now logarithm, and then we can try something different. Okay, so if I have function y equals ln x, although with ln x we would have the problem. No, wait. We should no. Oh, it would be. Oh, we need to start with this to get to ln x, of course. Okay, 1 over x. Okay, so this function looks like that. Now, let's just say I want to know what is the area below this function between 1 and 2. So, I calculate indefinite integral from 1 to 2 out of 1 over x dx. So we're getting natural logarithm of x. Of course, we don't need absolute value because we are on positive side of x-axis. And we got 2, 1. So this is ln 2 minus ln 1, which of course is 0. So this is ln 2. Okay, so I hope you can see how we are dealing with it. I don't think it should add you any more issues once you understand how to calculate definite integrals. The only thing left for you to do is to recognize appropriate part of the function below which you need to make your calculations. Okay, so now let's make our lives a little bit more complicated, but just slightly. So let's just say that now I want to ask you. Let's just say that we have two functions, y equals x and y equals x squared. Okay, this is y minus x. And this is y equals x squared. Look, both of these functions have two common points. Well, those two functions have two common points. Yeah, that's enough. 0 and 1. And look, now I don't want to know what is the size of the area below one of these functions. I want to know what is the size of the area in between those functions. So I want to know what is the size of this. Well, you might say, well, but we haven't had any formulas that would allow us to do it. We don't need to. We can use what we already know. How? Look, first thing I would do over here is that I would calculate the size of this triangle below y equals x. What is the size of this triangle? What is the area of this triangle? Well, this is, of course, is given by integral from 0 to 1 out of x dx, which is equal to x squared over 2, 1, 0, which is equal to 1 over 2 minus 0, 1 over 2. What would I do next? Well, next, I would calculate what is the area below x squared. So, now we are calculating this. So, this area is given by integral from 0 to 1 out of x squared dx, which is x to the power of 3 over 3, 1, 0, which is 1 over 3 minus 0, 1 over 3. Now, knowing this, how can I find this shape? This shape I can obtain by taking the triangle and subtracting from the triangle this shape, so I will get that this is 1 over 2 minus 1 over 3, right? Which is of course equal to 1 over 6. So you see here, by simply juggling our shapes and subtracting appropriate shape from a different shape, we will always be able to get what is the size of the area in between any two functions we want. Okay, let's just try one more case that is slightly more involved, but knowing what we know this far, I think should not give you any issues. Okay, so what do we need to do? Now the functions we've got is y equals x squared and y equals square root of x. Right, now, so we've got x, y, and, well, we've got y equals x squared and y equals square root of x. This function, of course, is given only for positive values. You cannot take square roots from negative numbers for now. Okay, and we get 1 here, 0 here, 1. Again, those two functions give two common points at 0 and 1. And I want to ask you, now, what is the size of the area between those two functions? Okay, I hope you know the strategy we should deploy in order to get this area. First, we should calculate the size of this weird shape over here. Right? So we need to first find this. So, how do we find it? Well, this is an integral from 0 to 1 out of square root of x dx. So this is integral from 0 to 1 out of x to the power 1 over 2, right? dx. So this is x to the power 3 over 2 times 2 over 3, right? 1, 0, which is equal to 2 over 3 minus 0, 2 over 3. So this, the area of this shape, 2 over 3. Now, the second step, it will be to calculate what we already know, actually. So what is the area below x squared? Alright, so we can do it quite fast, quite easily. So this is going to be integral from 0, 1, x squared dx. This is x to the power 3 over 3, 1, 0. This is 1 over 3. And finally, in order to obtain this shape over here, what we need to do is to subtract from the bigger shape the smaller shape. And we get that this is 2 over 3 minus 1 over 3, which is equal to 1 over 3. Okay, and this is it. This is basically how we calculate it. I just want to stop at this example. Look, what do we get from this is something like, I would say, very maybe not unusual, something very interesting. Look, if I'm going to take a square that we've got over here, and this is a square of the size 1, right? 0 by 1 by 1. And look, if I'm going to put quadratic function and square root, so two functions that are actually the inverse functions of one another in this interval, they would perfectly divide this, this square into 3 parts, each of which is the size of 1 over 3. Okay, does this have any significance to science? Well, I don't think so. But, like, when you think about it, well, the first time I saw it was when I was probably your age, when I calculated it in some mathematics class. Well, it gave me some cosmic order. That everything, you know, is in perfect places. Because you have two functions related to square. There are inverses. There are inverses of one another, and they take the square and they divide it perfectly into 3 parts. Each of them is equal to one another. Okay, but think about it. Think about it first. Okay, and this is almost over. The one last thing we need to do are improper integrals, and the improper integrals are going to be the topic of our next video. Take care.